Hello, welcome to this video. This is 4-4 and we are talking about curve sketching with extrema and points of inflection. This video is going to resemble what we did in Unit 1 when we sketched curves. So we're going to be using a lot of our pre-calculus knowledge about just general features of functions, and then we're going to build in what we've talked about this function with increasing, decreasing functions and concave up and concave down. Okay, so this video or this lesson is going to be split into 3 different videos. I'll focus on one example in each video. And yeah, so with that, we'll go ahead and look at our curve sketching recipe. So just to remind yourselves, the curve sketching recipe that we follow is first give the domain, reduce your functions to find vertical asymptotes and holes, give x and y intercepts, end behavior, and then check for symmetry, which is optional. That can help you graph. And then features 7, 8, and 9 are new for this unit. Well, really 7 and 8. Okay, we have to find increasing, decreasing, and with the relative extrema, and then also to find the concavity. Okay, and you'll notice about these examples is that they give you the function in all of its stages. I start out with f of x, then I have f prime of x, then f double prime, okay? So we get really excited when we see this because we don't have to calculate the derivative, which is nice. However, in examples that you'll be working on, you are going to have to calculate the derivative. You are going to have to calculate the double derivative, okay? So without further ado, we'll go ahead and look at this function, and we're talking about f of x here. And f of x is equal to 2x cubed over x squared plus 1. This is a rational function. Rational functions, denominator cannot equal 0. So we look at this and we say, okay, what value of x will make the denominator 0? And that's not possible, right? X squared plus 1 can never be equal to 0. So our domain is all real numbers, negative infinity to positive infinity. And then, which ties into our vertical asymptotes. Our vertical asymptotes, right? I don't have a denominator that is gonna be equal to 0, so we're not gonna have any vertical asymptotes. And since I'm not reducing or canceling any factors, we don't have any holes. You're like, well, what good is this example for? We're not doing anything. The next ones will have stuff. Okay. This one's gonna mainly focus on increasing, decreasing, and concavity. X-Intercept. Remember, an X-Intercept is when we take our function and we set it equal to 0, and we really don't have to worry about the denominator. If we multiply both sides by the denominator kind of disappears, and we get 2x cubed equals 0, and when we solve, we get x is equal to 0. So if we plug this in, our X-Intercept is at 0, 0, and which is also a y-intercept, right? That's at the origin. So I know that the y-intercept is going to be 0, 0, but I want to remind you to find your y-intercept, you just plug 0 in, right? 0, y here. And for this one, it's x, 0, right? Those are how you find those. Okay, so we get 0 when we plug in 0, and we get 0, 0. All right, end behavior. Remember that end behavior is your limit of the function as x is approaching infinity, as well as negative infinity. And what we do, especially with rational functions, is we look at the ratio of our leading terms here. So again, this is big over little, which means that there is no horizontal asymptote. Or sorry, there's no horizontal asymptote. We have a slant asymptote. So we're gonna have to do some sign analysis to go ahead and see, okay, what happens when I go to infinity. So when we plug this in, we're gonna get a positive infinity over a positive infinity. So I know that this is going to positive infinity. And then the limit as x approaches negative infinity, when we plug that in, the denominator is still positive. However, our numerator is negative. So this limit of f of x is equal to negative infinity. All right, symmetry. Our numerator happens to be odd, and our denominator is even, right? Odd is origin symmetry. It's a cubic. Okay, so that's going to flip across the origin, and then our denominator, even, that is y-axis symmetry. That's a parabola just shifted up 1. So an odd divided by an even is odd. So this is origin symmetry. We're going to see reflection across the origin. All right, relative max, relative min. Remember, we calculate these by taking the derivative. Okay, so I want to take f prime of x. So I'm going to take f prime of x, and I'm going to set it equal to 0 to find our critical numbers. Okay, so again, just like with our x-intercept, I can take the numerator, so 2x squared times x squared plus 3, and I set this equal to 0. Now, when I do this, we get two cases. We get 2x squared is equal to 0, and we get x squared plus 3 is equal to 0. This case produces 0. This case produces no critical numbers, right? That's what we're finding here. Okay, so I can take my number line, and we only have one. We have a 0 here. Okay, so we'll check -1, +1, and we're going to plug these into f prime, right? So f prime of -1, when we plug this in, okay, we'll get in our denominator that's positive times a positive, okay, and in the denominator that's also positive, so this is a positive value. Then I want to check f of 1, and when I plug this in, we have a lot of squares here, right? That keeps everything positive, so I have a positive outcome. Okay, so positive, positive. Well, what that means is it means that this is strictly monotonic. Okay, I'm never changing from increasing to decreasing. Well, what does that mean? Well, that means that we don't have any maxes and we don't have any mins. Okay, and then lastly, it says points of inflection. Okay, well, points of inflection occur when we go from concave up to concave down. So we're going to analyze f double prime of x. Again, I'm going to set this equal to 0. So I'm going to take f double prime, okay, -4x times x squared minus 3. And I'll set that equal to 0. Again, I'm just leaving off the denominator because when I multiply by the denominator to clear it, nothing happens. Okay, so we get -4x is equal to 0, which produces x is equal to 0. And we get x squared minus 3 is equal to 0. So x squared is equal to 3, which tells us that x is equal to plus and minus √3. So here is my sign analysis line. This is f double prime. And sorry, I want to make sure I label this. Here is f prime. Okay, and I have -√3, 0, positive √3. Okay, and we're going to go ahead and do some sign analysis with this. Okay, so and what numbers should you pick in? Again, 1s and 0s are always nice, so I'll plug those in, and then over here I'll just plug in a -2 and 2. Okay, and when we do this into our function up here, okay, so when we plug these in, our denominator is always going to be positive, right? No matter what x value I plug in, I get a positive denominator. Okay, and then I'll plug in -2. This gives me a positive. Okay, when I plug in -2 here, it's 4, so I get a +1. Okay, so that's positive, concave up. All right, then I'll do the same with -1. So when I plug in -1, this becomes positive. This becomes negative, so we have a negative. I'll plug in +1. Okay, this gives me a negative, and then in here I get a negative. So that is a positive, again divided by a positive in the denominator. Whoa, this thing is just C. Okay, we're good. All right, and then lastly for 2, we'll plug in 2, and we get a negative times a positive, which is a negative. Okay, so we're going concave up, concave down, concave up, concave down. All right, so all of these happen to be points of inflection. Okay, so what I'm going to do is we will evaluate these. Okay, what is f of negative root 3? What's f of 0? What is f of positive root 3? Okay, and what we get is we get these points. So negative root 3 is negative 3 root 3 over 2. We get 0, 0. And we get root 3, 3 root 3 over 2. All right, so let's go ahead and let's kind of sketch all this. Okay, domains all reals, no vertical asymptotes or holes. I have an intercept at 0. Okay, there it is. My end behavior is positive infinity as x goes to positive infinity. So I'm coming up here, and negative infinity as I come down here. Okay, and then we have points of inflection. Now our points of inflection are 0, 0, and then root 3, 3 root 3. So that's right about here. No, a little bit higher. Up here. So I'm going to erase my end behavior and adjust. Okay, and then this one's going to be right about there. Okay. All right, so always increasing, and then from negative infinity to negative 3, it is concave up. So we'll go like this. From negative infinity to, or negative root 3 to 0, it's concave down. So we get this going on. From 0 to root 3, it is concave up. Okay, and then from root 3 to positive infinity, it's concave down. Okay, and here is your graph. All right, so that does it for this example. The next examples, we'll throw in some more of that stuff. Okay, catch you next time. Peace.